Hello everyone again. So in this video we will explain the hardware. We will break down what we have attached here together and just give you a little explanation. This project is two pieces. One is a complete analog effect, which was my own senior project, which is integrated now with our digital system and its circuitry and everything that comes with it. And now we're going to go into detail of what each part is and what they do, and then we will give you sample sounds on the guitar and we'll change parameters so you can see how things work. Alright, so our analog effect has 4 different circuits in it. Excuse me, 5 different circuits in it. It starts, so this portion of the board is the analog effect. This circuitry here is a compressor, which basically brings the signal together and rounds the edges a little bit, makes the signal a little meatier. This board here is our distortion, analog distortion, and those 2 LEDs that you can see over there, those guys are the ones doing the clipping. And for you guys out there, if you didn't know, using LEDs to clip a signal kind of gives a little bit of emulation of a tube sound having rounder edges, actually using caps along with it. So it turned out to be a good sounding distortion. Next to it is a 2 circuit on this board. The first piece is a preamplifier and the second piece is a splitter, because we do split the signal to send it to the microcontroller. And our final piece is a 6-band equalizer, which has its own effects loop connections and is currently not being used at all. So that would be our analog piece, and up front is the interface, which has LEDs for each one of them, TP-DT switches to control the input-output of the signal and the power that goes through the board. So when you turn the signal off, it's a full bypass. It powers down the board. Also, it totally bypasses the signal, so it does not go through that board and it does not get degraded. And we have our jack connections. This is the input, the 2 split outputs, and the effects loop connections to the amp. And at the bottom is our power supply connections, which are fully isolated. We're using a bus G power supply, which has isolated outputs, meaning that amount of current running through one circuit is not going to affect another circuit, meaning that if you turn on all of the circuits, you will not draw too much current in order and actually get things in a dirty way, meaning drawing too much current on a power supply just puts noise on the signal. Okay, so that's that, and it has a little tiny board next to it which basically patches our so this was designed to be able to handle 2 amps, but if you don't want to, you can have one go to the amp and the other go to our microcontroller for the digital effects. So in this one we have that, and then we have a foot switch controller, which is the Marshall controller, and it's just 2 DP-DT switches which basically control the ground circuit that runs through the rest of the board. And when they come in, first we bring them to this circuit, all the switches, all the 4 switches. We have 2 single switches and 2 foot pedal switches that come to this board. The foot pedal switches get debounced with the capacitors, and we have 2 LEDs indicating they're on or not. And those are 2 being used for delay and flange. There is another circuit we have in here that is analog, but it's not being utilized right now. It will be very soon. It consists of a preamplifier and a 3-band equalizer. We do need to equalize the sound coming out of the microcontroller because we are experiencing a big degradation in the bass. And we do need to amplify the output a little bit. So this will be put in later on, and this tiny circuit next to it is the connections that we have with the board's extender through an extender connection, and we have our knobs and all the connections that go in. This, as we know, is the great Texas Instrument C5535 DSP processor, And it has a very good codecs for input and output. The ADCs and DACs used in these guys are high resolution and very good. And so we would like to in the future add a drum machine, which this is an MP3 trigger, which we will have a new set of switches controlling what drum line would you like to play, so you could play along with the drum line right here and there and not need anything else. Alright, so I think that is quite good for what we have here. Also, we are using a noise gate, but this is just on the amp because the power is just so dirty around here. Alright, so we will now demonstrate a little bit to you how these effects work. First, I'm going to turn them all off. When everything is turned off, we have a full bypass, meaning that the sound of the guitar goes basically through a bunch of wires and it will come out at the other end. So, first circuit I'm going to show you is the distortion circuit. Right now, we only have clean sound. When we turn on the distortion, and here's the one thing you need to know, that the distortion, analog distortion by itself is a lot more bass, is a lot more powerful. The fact that goes through the board, it degrades its bass, and that's something we have to figure out, and we're thinking the 3-band equalizer outside might help. But what we are thinking that the very low capacitance on the board is kind of a cause for that, and we're kind of losing our bass. So the first one is distortion, and then basically adding a little bit more volume. And the final switch is the one that bypasses the entire digital side. So when you flip that guy, now our guitar sound is going through the analog effect, but it's going through a loop through with the microcontroller board, meaning it's not being affected, but the mere fact going through being digitized and then passed back out degrades the sound, as you will see. So this is the sound we have with the analog. So we have a little bit of change in the sound, but it's not bad. And the fact that we use the digital to use the effects such as delay and flange, and they're used for solo stuff, so maybe the degradation of bass is not that important. Alright, so now signals coming through, and we're going to show you how we engage the delay and how we change the delay parameter for the time, and a couple of anomalies that we noticed. So as I'm making sounds so you guys can see the differences in the timing of the delay, Philip is going to show you how we make that change.
Alright, so there's the knob here is the one that's going to control the amount of delay, and simply move around this potentiometer. Right now what I did was I set that value to 0, so this is the minimum amount of delay. We actually can set that by flipping the switch momentarily. We don't want that on all the time because pulling that switch is going to drastically reduce the quality of the sound due to too much processing going on behind pulling that knob.
That's right.
So right now that is set to the minimum amount of delay. Go ahead and
so yeah, this is our fastest delay right now.
So that's a real quick delay. I'm going to go ahead and turn it up just a little bit to increase that delay time and pull that switch just longer. Kind of a lot of change there. Let's bump that up a little more. So we can
go all the way.
All the way?
If we go all the way, then there's so much delay that it will just take it a while to actually play, and it's not really practical, but this is how it sounds. Oh, no, you went the other way. Do a little bit less.
Technical difficulties. Okay, so that's 0. this was
Leave
not
it up.
happening
Leave it up.
early.
So not go all the way.
That is all the way.
Is it? Okay, so for some reason we're not getting that very long effect. But yeah, playing with the knob, we can change the amount of time on the delay, and that's one of the most things that is used for delay. So also, yeah, go ahead and explain the flanger too.
Okay, so the flanger, the same knob is, so the LED here shows that the delay function is currently being utilized. The other LED here shows flanger. So now the knob is being used to control the flanger effect. The knob is going to dictate how widely we want the pointer to oscillate. The wider it is, the higher and lower the frequency will deviate from what's being input. So right now we have kind of a fairly average value being fed into it.
So that the quality is degraded because there's more work being done on the flange. And this is one of the problems that the digital systems have to tackle with audio, is that any more work you do, you will degrade the sound. And our flange happens to be a little bit longer, a little bit bigger, even though we did everything we could to reduce it to be as short of a function as possible. So, do you have a new change? I'm gonna have to turn that up. It just has this wavy sound to it.
Yeah, it was more drastic.
Huh?
It was more drastic yesterday. I don't know what changed.
Yeah. No, just go all the way in. And if you put both of them together, then it's going to get something really weird. Okay, so this concludes our update for the moment. We will continue working on this and continue editing our algorithms and make the control software better, make the DSP algorithms better, and hopefully we'll find new ways to tackle everything else. Actually, we were going to implement a recording system on this, but unfortunately that is just not possible with this board because it has such a small onboard memory, and it's off-board memory on the micro SD is just too slow to record. So that was one of the goals that is impossible at the moment. So we just thought of it as being a fully digital effect system and not a recording system. But those will come up, so please wait for updates. Thank you very much.